Imagine if every puzzle on Earth was solved, every why that we have pondered but could not answer for all our trying be mastered. Imagine if we all, God's ways, could clearly understand. Will this be reality, or is it just myth? Our thinking is like the streaming colored lights, flames flickering across the dark northern night. It was dark before we started thinking, and it will be dark again if we stop. Some claim that most questions in nature have been answered. Others think that we have only just begun asking. This is their story, the story of the universe.
Plasmas are found virtually everywhere. They're found in solid state matters at very low temperatures. A flame of a match, a fluorescent light is a plasma. Fire in your fireplace is a plasma. The aurora obviously is a plasma. The sun and all of the stars are a plasma. Lightning is a plasma. In fact, 99.999%, as Alfvén used to say, of all observable matter in the universe is matter in the plasma state.
A plasma is an ionized gas. It means a gas consisting of charged particles rather than neutral particles, which is the constituents of a normal gas. The charged particles are electrons and atoms that lack electrons. So it consists of negative and positive particles that interact with each other by means of electric and magnetic fields.
The term plasma, as applied to electromagnetics, was first coined in 1923 by the Nobel laureate Irving Langmuir to describe the experiments that he was doing at the time. Basically, plasma consists of charged particles, the electrons and the ions or protons that we know in nature. It can also include charged dust. And in Irving Langmuir's experiments with the charged particles, he noted that they acted almost in a lifelike manner. They tended to develop cells. They acted very much in a way that indicated that they might somehow be related to life. And for that reason, he borrowed the term plasma from the blood plasma.
A plasma is like a society of individuals where all the individuals are interacting with each other through complex interactions like media, newspapers, television, and so on. And the normal gas is like a society where the individuals simply basically don't interact or interact at very short distances, very local communities.
The first effort to understand how plasma functions in the universe, to understand the plasma universe, was Christian Birkeland, who at the end of the 19th century wanted to understand what is the nature of the aurora. At this time, people were studying for the first time the nature of electrons. And you had, for example, the development of the cathode ray tube. The cathode ray tube we're familiar with. This is what powers our computers and our television screens. You have electrons accelerated, smashing into phosphorescent atoms in the screen and producing light. Birkeland reasoned that this might be exactly what's happening with the aurora. He basically felt that electrons coming from the sun would be channeled by the Earth's magnetic field into the atmosphere, where they would hit the atoms in the atmosphere, creating the fluorescent glow of the aurora. He wasn't content with just looking at this theoretically. He wanted to look at it experimentally as well. So he built a scale model of the Earth as a magnet. which he called a Torello, which was a metal sphere with a magnet inside. And he put it in a vacuum chamber, and he basically modeled the system of the aurora in the Earth's magnetic field.
Birkeland's way of thinking was in direct opposition to what I would call over-specialization in science. He was doing a lot of different things, taking patents. He was thinking about cosmology and about small practical things. He was creating industries and so on. And I think the main power in his ideas when it comes to inspiration is in particular this.
After his death, this whole approach of seeing the universe, as Birkeland put it, as filled with all sorts of charged electrical particles, basically fell away. He didn't have descendants, intellectual descendants who would pursue this avenue of approach. His approach, which is similar to that of many of the Big Bang theorists today, was to take a purely mathematical approach and say, what is the simplest way to express phenomena mathematically? And basically, let's try and fit the phenomena into that simplest mathematical expression. Well, he found that it was very difficult to precisely define the sort of mathematical three-dimensional currents that Birkeland had hypothesized. Remember, this is long before the development of computers. So he found that the easiest mathematical representation was if the currents were all confined to a sphere that extended little beyond the Earth's atmosphere. And therefore he started to model things on this model, which completely contradicted the idea that these currents flowed from the sun and were trapped in the three-dimensional structure of the Earth's magnetic field.
Hannes Alfvén simply felt very much in spirit with Birkeland in this respect. Hannes Alfvén was an engineer from the start, and he liked to think about everything as an engineer and not in very abstract terms.
And he realized that it would be impossible for electrons alone to flow from the sun to the Earth. It had to be plasma flowing, because if the sun gave out a flow of electrons, eventually it would become positively charged, and that would prevent the flow from continuing. So his theory was that there were ejections of plasma from the sun. When these blobs of plasma hit the Earth's magnetic field, they would distort it. And if the distortion was enough, you would have things called magnetic storms.
It took many years before Alfvén's work in this area was recognized. And the main reason is that his work was so simple and so obvious that even the brightest people did not really realize the impact what he was doing.
He also developed at this time a more elaborated theory of how the electric currents concentrate themselves. Because of course, when you look at the aurora, it isn't just a continuous glow. It's this fine sheet of filaments. And these filaments, Alfvén knew, occurred because of what's called the pinch effect, which is if you have currents flowing through a plasma, any plasma, the currents produce magnetic fields. The magnetic fields interact with the currents in such a way that currents are attracted to each other. So if you start out with an even distribution of current, the current will filament. It will become tiny concentrated filaments of current pulled together by their own magnetic field.
The essence of magnetohydrodynamics is to boil down the very complicated motions of plasma particles in magnetic fields into a simple model that visualizes the plasma as a fluid that is electrically conducting. So it simply is a fluid where currents are allowed to flow, and the currents are interacting with the electric and magnetic fields and dragging the fluid with it. Another way to see it is that the fluid is dragging the magnetic fields with it. And this simple picture, to visualize things, had an enormous impact on how we could understand phenomena in space.
So he developed this pretty elaborated theory, which was compared with both laboratory experiments and observations of how the aurora works. But Chapman was still the dominant theorist, and Chapman completely rejected his theories, and in fact wouldn't even discuss it with him. Hannes Alfvén is generally credited as being the father of modern plasma physics. And he was, of course, awarded the Nobel Prize in 1970 for his extremely varied work in plasma physics. Now, by the time that satellites and space probes had begun to demonstrate that Alfvén and Falthammers and his colleagues' ideas about currents flowing through the solar system were correct, that such currents really did exist, and people began to accept that these currents, much stronger currents during the early days of the solar system, actually had a role in the formation of the solar system, in compressing gas and dust down to form both the sun and the planets. By that time, Alfvén had started to move on to larger scales.
Alfvén was very eager on formulating very bold theories for cosmology, and basically rejected the Big Bang model, and in this way came very much in opposition to the mainstream of cosmology.
Because he reasoned that if these currents flowing through the solar system could have formed the stars and the planets, then could not have much larger scale currents also be the way that galaxies themselves form. Some people have said that science is a method for asking questions of nature. And if that's true, then we can say the Big Bang supporters are people who won't take no for an answer.
Over the last 2 or 3 decades, the Big Bang theory has become increasingly more and more speculative. One expects from a scientific theory definite predictions which can be tested by observations. If the observations disprove the predictions, that theory is supposed to be disproved, and it should be modified or abandoned.
In science, we work from observation, from empirical observation that starts in the here and now and works outwards and backwards. The Big Bang starts from mathematical formulas, deductions, that start from the beginning of the universe and to try and predict it forward. This is the same mathematical approach, mathematical deductive approach, that led 2,000 years ago to the development of the Ptolemaic universe. The universe, of course, which was Earth-centered, with the planets going around the Earth, with the stars in a crystalline sphere. What these theories have in common is that they try and derive what should be the universe based on what perfect principles we can develop, what God should have made the universe to look like. And then they try to fit the universe into that perfect framework.
However, what has happened over the years is that whenever observations have come up which don't agree with the predictions of the Big Bang theory, the theory adds an extra assumption which is not at all tested, which is not at all resting on conventional physics, and simply assumes that that must be true.
The problem with that is that develops myth, not science. It develops a religious faith in which nothing in the real world, in the observable world, can contradict the faith in this structure, in the Big Bang. This undermines the entire scientific enterprise. The reason science has been valuable to human beings is because it allows us to predict nature in such a way as we can use nature in a predictable fashion in technology. To abandon this approach, which has served us so well, and to go to the idea that we can deduce, we can read the mind of God, as Stephen Hawking says, and deduce from perfect mathematical principles what the universe must be, is to abandon the scientific method.
There are those who would say that the story which follows could happen only in a dream. Regardless of where it could happen, this is the way it did happen, in this rather strange and out-of-this-world office. Whitey is entrusted with the records of good salesmen. Red, the other kind. Now, it seems that Red and Whitey never see eye to eye on matters. Naturally, this leads to many arguments.
I am the door. By me, if any man enter in, he shall be saved. There is only one door to heaven. People would have us believe there are many doors to heaven. No one can enter with a heart of unbelief. Only a heart that believes will have entrance there.
I'm going to keep a pretty close watch on these guys.
And so am I.
This idea of the Big Bang, which did originate at the beginning of the 20th century, the reason why it is so widespread nowadays is that it has a deep connection with the biblical creation. Instead of saying that the universe was created by God like 4,000 or 6,000 years ago, they now say it was created 10 billion years or 20 billion years. So for most people, and also for many scientists, they see a connection between this creation which comes from the Bible and this scientific point of view.
In 1952, in August 1952, we had a meeting of the International Astronomical Union in Rome. And we were received by the Pope. The Pope was then Pius XII. And Pius XII made an address to the astronomers. And this address was very clear. He said, oh, the Big Bang is the Fiat Lux, and how beautiful is the astronomy, how it proves that the greatness of etc., etc., etc. And I've been always sort of an heretic in all that sort of things. I don't believe in any God. And having the Fiat Lux and the Big Bang associated each with the other made me suspicious from the very beginning.
Nowadays, the majority of the physicists and astronomers, they believe and they work with the point of view of the Big Bang, according to which the whole universe did originate out of nothing, like 10 or 20 billion years ago, in a Fiat Lux, in a moment of creation. There was nothing before, and then the whole universe did appear and then begin to expand and to grow, and our galaxy, our life came out of this great explosion in the past. But I myself I had always problems with this point of view because they are somewhat against the principles of physics, the most basic principles of physics, which are related with the conservation of matter and conservation of energy.
Yeah, I forgot completely about the Big Bang because it just didn't interest me to look in those distant things of which the physics was rather vague and difficult to observe. But let's face it, in all the story of astronomy, for years and years and centuries, the progress came from new observations. And from confrontation of those new observations with past theories, contradictions, sometimes no contradictions, sometimes just a confirmation, but most often the contradictions led to new progress, to changes in the theories.
In standard Big Bang cosmology, you have what I call a series of epicycles. The Greeks used to have epicycles, which are known as circles whose centers move on other circles, whose centers move on other circles, in order that they could correctly describe the position of a planet at any given time. They found that in some cases they had to introduce many circles before they could get anywhere near the reality. These epicycles are the assumptions that have been put in ad hoc into the theory from time to time.
The way that the Big Bang has handled the cosmic microwave background is a very good example of how this process works. When the cosmic microwave background was discovered in 1964, this very smooth, even radio radiation coming from all directions at once, the smoothness of the microwave background was considered a proof of the existence of the Big Bang. Only a universal explosion, they argued, could create this smooth, even background.
Now, this is not necessarily so. Actually, the 3-degree radiation, to me, has not a cosmological value. It is observed in any cosmology. In any cosmology, you can predict the 3-degree radiation. So it's a proof of no cosmology at all if it can be predicted by all of them.
There's no explanation at all of the microwave background in the Big Bang theory. All you can say for the theory is that it permits you to put it in if you want to put it in. So you look and it's there, so you put it in. That's that. It isn't an explanation.
First of all, the temperature of the microwave background, basically the amount of energy, was not what the Big Bang supporters had predicted. They had predicted a much higher temperature.
So it was 50 degrees Kelvin that was being compared against the 2 to 5 degrees Kelvin from the steady state universe. Now, this may not sound like much, but in energy density, where we measure the absolute differences, the differences is 4 orders of magnitude, 10 times 10 times 10 times 10 difference. So there is an enormous difference between 50 degrees Kelvin, a rather poor indicator of what is happening in the universe, and 3 degrees Kelvin.
When you read the textbooks, they don't tell the whole story. They don't present these figures, 5, greater than 5, 7, 50, and then that they did find 3. So that's very strange how the textbooks, they hide a part of history.
And the temperature of the Big Bang proponents was rapidly readjusted from 50 degrees to 3 degrees.
But their theory could be adjusted so that the temperature becomes a free variable that you just taken as what was observed.
We have an observable universe which is made of stars, galaxies that are not very distant, and that's all, because the 3-degree radiation, I would even think that it might be local. Still not. And going beyond that is, I think, a wild extrapolation, whatever it is. And the physics that we could imagine to be existing there is based on nothing, because we have no test for it.
Although Big Bang advocates claim the discovery of the cosmic microwave background radiation as conclusive proof of their theory, history actually shows that there is a long line of well-hidden predictions previous to those made by Big Bang theorists. Not only were these predictions prior to those of Gamow and associates, but more importantly, they were made without any need for an expanding universe, and with far greater precision. This shows us that observations such as the background temperature of space have no preference for one or another theory, and therefore may not be used as definitive proof of any particular model. The fact that a theory is able to describe an observation does not mean that the observation proves the theory.
This is Bob Wilson at Bell Laboratories. The noise you're listening to is noise from a radio astronomy receiver on the 20-foot horn reflector antenna. This is the original instrument with which Arno Penzias and I discovered the cosmic microwave background radiation in 1965. This radiation comes from all directions and has a thermal spectrum. It sounds, therefore, very much like the noise you would hear on an FM set or a TV set which is tuned to an unused channel. Unfortunately, only about 10% of the noise you hear is coming from the cosmic microwave background radiation. The instrument is contributing about 22 degrees of noise. The Earth's atmosphere is contributing another 4 degrees. Our Milky Way galaxy is contributing 1, and finally the cosmic microwave background radiation, another 3 degrees.
When you say that the microwave background is a perfect black-body radiation, that means it is completely thermalized. The theory of black-body radiation tells you that that is the ultimate state of radiation when all information of sources from where radiation came has disappeared. Because thermalization means that it's completely smoothed out, wiped out its sources.
One of the main things that people point to as confirmation of the Big Bang as a valid theory is its predictions of abundance of the light elements. That this confirms that the theory is a good theory. But in fact, it doesn't. In fact, observations clearly contradict this prediction of the Big Bang. Big Bang predicts the abundance of 3 elements: helium, lithium, and the isotope deuterium, which is the heavy isotope of ordinary hydrogen.
Now, one of the conclusions from this particular hypothesis that you can make deuterium in the Big Bang was that the density of matter in the universe should not exceed a certain value. Now, over the years, in the 1960s, this seemed to be holding out. 1970s, it seemed to be holding out. But by 1980s, it had become clear that the universe has considerable amount of dark matter, which is not included in these calculations. Now, if you include all this dark matter, you exceed the limit that deuterium abundance has put. That means if you assume that all the dark matter is present, then you could not have made deuterium in the amount that is observed in the universe. So this was a way of saying that the Big Bang prediction was wrong.
To determine the density of the universe and see whether this is consistent. If the theory is right, the density of the universe determined from deuterium abundance, the one determined from lithium abundance, and the one determined from helium should all be the same number. There can only be one density of the universe. Well, actually, that's not true. Again, these are gross contradictions, and yet again, it doesn't cause the abandonment of the theory. Big Bang theorists simply say, well, there must be something that we don't understand about the evolution of lithium, about the evolution of deuterium, and even though these predictions have steadily diverged over the course of time.
But what did the Big Bang proponents do? They wanted a way out, so they said that this extra matter, which is proving to be awkward to fit into the framework, has to be a strange kind of matter, which is often called non-baryonic matter. Non-baryonic matter is basically matter which is not made of protons, neutrons, and the kind of elements that we are made of here on the Earth, or which we see in the stars or in the interstellar medium.
Dark matter. What was dark matter? Dark matter was some matter that we don't understand, we don't know what it's about, we haven't observed it, but it isn't ordinary matter, so it doesn't enter into our equations about the light elements, and we can't see it as stars. But dark matter is 90 or 99% of the mass of the universe. This is what we call in science a fudge factor. When your equations don't work out, you just write in this little plus something. Well, in this case, this was a humongous fudge factor because it was 90 or 99% of the universe.
And you have to not only postulate that this matter has to exist, but it has to exist in quantities much greater than the amount you see of ordinary matter.
And I should emphasize that people have looked for dark matter. People have looked for dark matter since it was proposed 20 years ago. Axions, WIMPs, little particles that are supposed to be floating around in space that we should, in theory, be able to observe as they pass through the Earth. Dozens of experiments have looked for these particles. Not one has been found. Again, this should be a contradiction. The way science works, you make a prediction, observation contradicts it, the theory should be rejected. But that hasn't happened. And the epicycles don't end. There's a problem with dark matter, even theoretically. Even though we can't observe it, there's still a problem with it, which is dark matter slows down the expansion of the universe. So the length of time that the universe has existed, the length of time since the Big Bang, should be shorter than what's indicated just by linear expansion. The problem is it's too short. The prediction of the cold dark matter theory is that the universe should be about 8 billion years old. Well, that's a big problem. We can determine the age of stars in our own galaxy, in the oldest globular clusters, both based on very well confirmed theories of the nuclear evolution of stars and spectroscopic observation. And the stars in our galaxy are 13 or 14 billion years old. So it's very embarrassing to have 14 billion year old stars in an 8 billion year old universe.
In addition, they went into dark energy. Now, why did dark energy come in? Because if you take the present value of the cosmological constant and the cosmological constant which came out of inflation, you find that they are not the same. Not only they are the same, but you have to find that the difference lies in something like 108 orders of magnitude. Now, can you imagine a physical theory getting the answers wrong by a factor 10 to the power 108? Yet, the Big Bang cosmologists very coolly accept this and simply put in another epicycle by saying that there is a dark energy which has changed over the time by this factor. So we have to accept that.
Dark energy is some force, again, unknown on Earth, unpredicted by any theory that we have validation of here on Earth, that causes an acceleration of the expansion of the universe. So as the universe is accelerating, and it's older than it appears on the basis of the dark matter theory, and it's 15 billion years old. So we solve the problem of the age of the universe by hypothesizing yet a third completely ad hoc epicycle dark energy. So now we have a universe which is 70% dark energy, 28% dark matter, and only 2% matter that we can observe through our telescopes and here on Earth. Epicycle is being piled onto epicycle. And in the process, what we call the predictive power of the theory is fading away to nothing. One of the most destructive features of the methodology of the Big Bang is that it conveys the idea that only experts can understand the universe. Only people versed in extremely complicated mathematics can understand the universe. That if dark matter, dark energy appear to be incomprehensible or even nonsensical, it's because you don't understand the mathematics of these complex equations. This is, of course, the argument of the emperor's new clothes. If you can't see the emperor's new clothes, then you must be either stupid or incompetent.
So this goes on, and we can find that the old Greek tradition of epicycles, which was even adopted by Copernicus and has been continuing in standard Big Bang cosmology. If we go by the history, the Keplerian orbits, which were elliptical orbits, very cleanly and neatly resolved the problem of planets. And the circles upon circles idea had ultimately to crumble down. Now, in the same way, I suspect that the Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.
Does this mean that the age of the universe is not what Big Bang theorists have implied? Could the universe be eternal after all? How much are cosmologists really able to know?
We are now in a stage which can be called a plasma universe. And we are simply not privileged to know what stage the plasma universe evolved from. We do not have privilege to that information. We do not know. We will never know. And this is one major difference between the plasma universe cosmology and the Big Bang cosmology that claims to be closing in on the final answer.
The universe described by plasma cosmology is quite different. Here we are talking about a universe with no beginning and no end, an infinite universe, continuously evolving, an evolution that is continuously increasing at an ever rapid pace. It is a universe in which there is a coherence between what we can understand in the here and now on Earth and what we can understand in the rest of the universe. A universe in which there is no real limit to our ability to understand more new phenomena. And a universe in which we can apply what we learn in the universe in present-day technology.
The basic difference between plasma and all other forms of matter, that is solid liquids and gases, is that a plasma produces electromagnetic radiation and also tends to filament. So that we would expect in a simulation, which is what we see, in an experiment, which is what we see, we would expect to see throughout the cosmos a filamentary structure that is a spaghetti of currents intertwining the cosmos.
We can use plasma theory derived from experiments in the laboratory, from the basic concepts of plasma instabilities, from Maxwell's equations, and from the well-known laws of gravitation, to describe and predict how the structure of the universe came into being and what that structure is. So the key question is, how could this structure come into existence? Now, in the Big Bang theory, the universe starts out extremely homogeneous, very smooth.
This was in direct contradiction to the plasma universe that insisted that the universe overall must be filamentary.
But what we have today is extremely clumpy matter. When I talk about these huge voids, the structure of voids, the matter inside the voids is less than 10%, perhaps less than a few percent as dense as the average. And the matter in the walls of these voids, where these filaments of superclusters of galaxies are located, is 10 or 20 times the average. So you have extreme clumpiness. Now, what's the problem for the Big Bang to explain this? There's a huge problem. There is not enough time since the Big Bang to form these structures. These structures are older, much older, than the time hypothesized since the Big Bang.
Now, again, in interpreting the observational information, we can again go to the laboratory, which we are privileged to diagnose in any number of ways, in any number of directions, and run any number of experiments, which you can't do with the universe. But we also turn to the supercomputer simulations. Now, what a simulation does is that it allows you to model the plasma, regardless of size, put in the rather few basic initial equations, and then follow the simulation through its various nonlinear stages and the different morphologies or shapes that the plasma will take.
In Tony Peratt's simulations, as the current spirals into the center of the galaxy, it turns around and moves out along the axis of the galaxy. In that central area where the current is extremely concentrated, there seemed again the potential for violent events. And Alfvén and Peratt raised the question, couldn't this be a way of explaining the extremely violent events that occur in the center of galaxies that are known as quasars, in which huge amounts of energy are released in what, by astronomical terms, is a relatively small amount of time. That is, millions of years compared with the billions of years galaxies exist.
Initially, the time frames shown represent 1 billion years or so, but now we're going to carry it out for 10 billion years to see what happens to these double radio galaxies or quasars as the two filaments have evolved into. And you'll see that the tails start to elongate, and fairly soon you're going to start to see a spiral structure. And as we get closer to 10 billion years, the end of the movie, you will see that we have formed the shape, the morphology, the shape of a spiral galaxy.
Now, Alfvén developed a number of concepts that were critical to the whole understanding of the plasma universe. First of all was the basic concept of scale invariance in plasmas. That means there are certain phenomena in plasmas that don't change regardless of whether you're dealing with a laboratory scale of centimeters or a solar system scale of millions of kilometers or a galactic scale of hundreds of thousands of light years. What that meant was that time scales the same way as distance does. So not only does this mean that the phenomena of the cosmos can be studied in the laboratory, but because of time compression, phenomena of the cosmos are essentially transient phenomena. It's funny to think of a galaxy lasting billions of years as a transient phenomenon, but it's analogous to events in a laboratory that last only millions of seconds. Another way of putting it, the plasma universe is extremely dynamic.
It's not going to be hypothesis. We've moved further than hypothesis. We've definitely gone into the second lake, the analysis, and we're well towards the third lake. Now, we haven't reached the third lake, of course, and perhaps, well, you can't with the universe because you can't experiment with the universe itself. Now, of course, like Alfvén, his idea, indeed you can determine what's happening in the universe in an experiment, but as far as producing universes, well, we're not going to do that. So we're going to do the best we can in the laboratory.
The universe that the Big Bang envisions and the universe of plasma cosmology are very different universes, and they have very different implications, and they cohere with very different ideologies of what is happening here on Earth.
The Big Bang theory will collapse under its own weight of assumptions, and a more neat theory, neat interpretation of the universe will emerge.